Okay, now we're doing 4.2 exponential functions, and I'm going to skip the warm-up because I want that area to do like a general overview of an exponential function. The general formula is y equals b times x minus h plus k. Okay, and h and k are just like they've been in other formulas. H shifts it left and right. And remember, x is always lie, so h is always the opposite of what it looks like. And because you're subtracting it, k will shift it up and down. Okay. On b, if it's negative, it reflects over the x-axis. Okay, and then if you look at the number in front of you, whether the absolute value of it. Okay, so you're not looking at whether it's negative or positive, you're just looking at the number. If it's less than 1, it's going to be a decay. And if it's greater than 1, it's going to be growth. And sometimes that decay, that less than 1 might be a fraction, sometimes it's a decimal, but if it's less than 1, it's decay, if it's greater than 1, it's growth. Okay, so those are the main parts. Once you have your parent function, those are the way the parent function shifts. Okay, when we start to graph it, our parent function ordered pairs that we're going to graph are always going to be 0, 1, and then 1 comma b, and b is your base. So for this one, my base is 2. So my parent ordered pairs are going to be 0, 1, and 1 comma 2. Okay, and this isn't being shifted at all. This is the parent function that we're graphing. And so I'm going to graph 0, 1, and 1, 2. Okay, and that shows you that it's going up to the right. My axis of symmetry is going to be y equals 0. Okay, because up here, my k is my asymptote. I forgot to write that up here. So y equals k is my asymptote. So here, because I don't have a k, that's why y equals 0. And I'm just going to put that in as my asymptote in as a dotted line. Okay, so I know that it's approaching my asymptote and it's going up to the right. So it's going to go, you really only need those 2 points. It's going to approach on this side and it's going to go up exponentially to the right. Okay, my domain on all of these is going to be negative to positive infinity. This is for exponential functions. And then my range is from 0 to positive infinity. And if you look at it, it's going from the asymptote up to positive infinity. So your range is really going to be tied to your asymptote every time. And that gives you everything that you need to know is to graph it. This is going away. It grows away from the asymptote. And I don't want you to think about it going up or down, because when we start shifting it around, then that's not gonna work anymore. So it's growing away from the asymptote. Okay, since the parent function is growing away from the asymptote, that's growth. Okay, from left to right, it's growing away from the asymptote. So that's a growth function. Okay, next, going to number 2. Okay, so we're taking the same parent function. Our base is 2, right? And this time we have a k. My k is 3. I don't have an h. If I had an h, it would be up in the exponent with the x. So I don't have one. My k is 3, so that means it's going up 3 from where it was. All right. My parent ordered pairs would have been 0, 1, 1, 2. That's our parent. And it's shifting up 3. That means my y values are always going up 3. So after it shifts, I'm going to have 0, and then 1 plus 3 is 4. and 1, and then 2 plus 3 is 5. So the x values aren't changing at all because I'm not going left and right, but because I'm going up and down, my y values are going to go up. I'm adding 3 to my y values. So it's going to be 0, 4, and 1, 5. My asymptote now is y equals 3 because I have a k value, and I'm going to go ahead and put that in. So I know it's going to approach that asymptote and go off to the right. Okay, so all it did is, and that makes sense, it shifted up 3. That's my parent from the previous one. My domain for exponential functions is always going to be negative infinity to positive infinity. And my range is based on my asymptote. So my range is going from 3 up to positive infinity. Okay. Number 3, we've got a couple of different things going here. We do have a k, so we know it's going up 2. We also know then that our asymptote is that y equals 2. Your asymptote is always y equals whatever your k value is. And then with the x, I'm subtracting 3. So my h is a positive 3 because x is always lie. It's the opposite of what it looks like. And that means I'm going to go right 3. So that's how my parent function is shifting. So my x value is going to go right 3. My y value is going to go up 2. So if my original parent function is 0, 1, 1 my base, which is 2, and I can do left and right and up and down shifts at the same time. So I'm going to do that here. So if I'm adding 3 to my x's, so 0 plus 3 is 3, 1 plus 3 is 4, and I'm adding 2 to my y. So 1 plus 2 is 3, and 2 plus 2 is 4. And so I'm going to go ahead and graph those. I've got over 3 and up 3, and over 4 and up 4. My asymptote is y equals 2. Always get your asymptote in there before you draw your graph so you know where it's approaching. And so I know it's approaching this, and then it's going off and to the right. Okay. As always, our domain is negative to positive infinity. And my range is based on your asymptote. It's going from 2 to positive infinity. Okay, so that was when we had a base of 2. And that the 2 was bigger than 1, so that's why it was growth, and it was growing away. Okay, and I'm going to go back here and talk about this. And we said that if our b was bigger than 1, it was decay, or smaller than 1, it was decay, but bigger than 1 was growth. Our base was 2 on all these, so that's why it was growth. Okay, our next one set, our base is going to be 1/2. That's less than 1. Okay, so our b is less than 1, so you know that this should be a decay problem. All right, so just have that in mind. Our parent function for this is 1/2 x, so my parent ordered pairs are 0, 1, and 1, 1/2. Or 0.5, you can do either way. So I have over 0, 1, and 1, 1/2. Notice it's coming back the other direction. I don't have a k, so my asymptote is y equals 0, so I'm back here. Okay, so this time it's coming down, it's coming down this way back towards the asymptote, this direction. Okay, my domain still is always going to be negative to positive infinity. And my range is based on my asymptote, which is from 0 to infinity. Okay, and we talked about how this was going to be decay. And you also can tell that it's decay because the parent is growing towards the asymptote. And you're talking about what the parent does. The parent is growing towards the asymptote, so it's a decay problem. But we knew it was going to be decay because our b was less than 1. Okay, next one. Same base. We have a base of 1/2. This time we have a negative in front. We haven't done that yet. We don't have an h or a k. We're just focusing on that 1/2 in front of it, or the negative in front of it. And we talked about how if we have a negative b, it's going to reflect over the x-axis. I'll get that written here. And that means you're going to change signs of all your y values. Okay, so if my parent, if my parent ordered pairs are 0, 1, and 1 1/2, then my shifted ones, right, all I'm doing is reflecting over the x-axis, so my x's are going to stay the same, but my y values are all going to become negative because I'm reflecting over the x-axis. So, and then again, I don't have a k, so my asymptote is y equals 0. Put that in there. And then I've got 0, negative 1, and then 1 and negative 1/2. And that kind of makes sense because if you think about the last one we did, this is just taking that last one, which was our parent, and flipping it over the x-axis. My domain always for exponential is negative infinity to positive infinity. And on this one, my range has flipped though because it's below the asymptote. So it's going from negative infinity to 0. Okay, remember that it's always from bottom to top. So be really careful of that when it goes on the other side. Okay, and this one, we didn't really talk about this one in the model, which is why I wanted to bring it up here. And this time I've got a negative in my exponent. This reflects over the y-axis, which means we change signs of our x values. Okay, and I'm on these bases, I was just focusing on the reflection, so I don't have an h or a k. So my asymptote is still y equals 0. Okay, if my parent function is 0, 1, and 1 in my base, which is 1/2, then the reflection, I'm changing the signs of my x values. Well, the opposite of 0 is still 0. And then I'm going to have a negative 1 and 1/2. So this is going to be 0, 1, and negative 1 1/2. And my asymptote is y equals 0. Okay, and this is going to look like this. Now, this is where things get confusing sometimes when they're talking about growth or decay. This looks like growth, but determining whether it's growth or decay depends on what the parent function does. And if you go back to number 4, that was our parent function. Our parent function is growing towards the asymptote, so it's decay. The reflection just is moving it around. So don't base your growth or decay on what the end, it's always based on your parent. And then domain is negative infinity to positive infinity. And my range, it's going up, it's above 0, so it's from 0 to positive infinity. Okay, so those are all exponential functions. You're going to find when we have these formulas of the h and the k always have the same effect on our functions. And so that kind of helps that you have that consistency in how we apply it. Okay, next part we're going to talk about is exponential functions with respect to interest. And the general formula for interest is y equals a b to the x. Okay, your a is your initial amount. That's how much you start with. Your b is either going to be 1 plus your rate or 1 minus your rate. And x is the number of years. And this is just for simple interest. There's no compounding in this. Okay, whoops. Okay, so my rate is always going to be whatever my percent is, and you're going to change it to a decimal. And you move the decimal places 2 to the left, but if that confuses you, just whatever your rate is, just divide it by 100 and you'll have your decimal. So this is 0.04 is my rate. Okay, so if I'm setting this up, they bought the Altima in 2010 for $25,000. So $25,000 is what we started with. So that's my A. Oops. And then it's inflating. Okay, so inflation means it's going up in value or in cost because its inflation goes up. We've all been seeing that. So it's 1 plus 0.04 to the x. This is a model that you'll use for different situations. I want you to go ahead and combine whatever's in the parentheses. So I have y equals 25,000 times 1.04. Whoops, my computer's getting hot. 0.04 to the x. Okay, that's my model for that situation, for the $25,000 Altima that's going up at 4% every year. Okay, the next question wants to know what we would pay now due to inflation. And in my notes, I calculated it for 2020. That's okay. In the next one, I'll do 2024. So my X was 10 years. And so I'm going to take my model, my Y equals 25,000 times 1.04, and I'm going to take it to the 10th, because from 2010 to 2020 is 10 years. So we're finding out what the cost is going to be in 10 years given that growth rate. And remember that in real life it doesn't always go at a steady percentage every year, but we're just using that for understanding how it works in exponential form right now. Okay, and so if I do that, you're just going to literally put it in your calculator, 25,000 times 1.04. Remember, you use a caret to raise it to the 10th power. And I want you to go ahead and do it. Make sure you get the right number. It should be $37,006.11. Okay, so a car that cost $25,000 in 2010 at only 4% inflation is going to cost $37,000 10 years later. Okay, so 4% doesn't sound like big inflation, but that's a big difference in the cost of a car. Okay. The next part takes the same car, okay, and inflation goes up, but when you buy it, the value of it that you can sell it for actually goes down. Okay, so that's talking about like the cost of a new car goes up, but the actual car itself goes down in value as soon as you drive it off the lot. And this is telling us that it goes down by 8% each year. Okay, and if I make that a decimal, it's 0.08. And we're still starting at 25,000 in 2010. My model is going to be y. Remember, we're using y equals a. My b is going to be 1 minus r to the x because depreciation goes down. So it's going to be y equals 25,000 times 1 minus 0.04 to the x. And go ahead and fix whatever's in that parentheses. So I have 25,000 times 0.92 to the x. That's my model for the depreciation of the car. And then I went ahead and calculated it for 2024. So in 2024, that would be 14 years from 2010. So we're going to see what the value of that car is after 14 years. So, and again, remember, it doesn't go down exactly by 8% every year. It actually goes down by the most percentage at the beginning of the contract and then goes down by less as time goes on, which is why it's usually a good idea to buy a car after the first year or two, because most of the fastest decrease in the depreciation is that first year or two. But we're just using a constant depreciation for this. So we've got y equals 25,000 times 0.92 to the 14th power, and I came up with 7,779.82. So from 25,000 to just under $7,800 in 14 years. Okay, so that's how our interest works, and that's all we've got for this section. Thanks.